Introduction to Electrostatics. All right, so there are a few concepts that we want to go over. The concept of a charge, charging by friction, charging by conduction, induction, and eventually we want to end up with difference between insulators and conductors, and then eventually we want to end up with Coulomb's law. So let's start with the concept of charge, and it goes all the way down to the atoms. So for the atoms, and I'm going to try to make this a brief overview of the concepts. There is a worksheet on Canvas that you can access and try some of the problems. So this is just purely conceptual, no math, no calculations yet. When it comes to the atom, what we have here is, well, so we have the nucleus. In the nucleus you'd have some positive charges, these would be the protons, and you'd have some neutral charges, so you'd have some neutral particles, these would be neutrons. I'm just going to indicate it this way, and this would be the nucleus, and then you'd have the electron somewhere on the outside. And typically the way this is drawn is that you place some kind of a negative here, and then you indicate that this negative orbits the nucleus. Let's maybe put another electron somewhere here, and then this electron orbits the nucleus. Now parts of this picture are true, and then parts of this picture are not true. So what's true is that we do have the nucleus, and then on the outside we have the electrons. What we don't really know is what the electrons are doing. So when we say that the electron is orbiting the nucleus, that can't quite be the case. For the following reason, at least from the perspective of the classical physics, whenever you have a charged particle and the charged particle goes along a curve, it emits light. So let's say you have a nucleus, positive nucleus, and then you place a negatively charged particle somewhere here, and then you're going to make a claim that this thing moves along a circular or some curved path. If this is what happens, some speed v, then you have a centripetal acceleration. It would be a centripetal acceleration, and that acceleration would be pointing towards the center. So you'd have some AC. If it's not a circular path, then you'd also have some sort of tangential acceleration. Be it as it may, you'd still have, as long as the particle moves along the curve, you would have some acceleration. Now, whenever charged particle moves along, whenever charged particle accelerates, it will emit electromagnetic waves. Now, it's not something you know yet, or maybe you do, but we haven't covered that yet in the class. Still, a charged particle that accelerates will emit light. Now, if it emits light, electromagnetic radiation, if it does that, then it loses energy. If it loses energy, then its orbit must change, right? If it loses energy, then it slows down. Now if it slows down, then the orbit, and as it continues to orbit, it continues to emit energy, and so it continues to slow down, its orbit would look like this eventually. It would just spiral in. So if we did have an electron that did actually move along a curved path around the nucleus, then that electron would necessarily have to collapse into the nucleus, and we wouldn't have atoms. There would be no atoms if the electrons were to just simply orbit. So that picture cannot be true. Electrons can't really orbit the nucleus, at least from the perspective of classical physics. And then now what are the other options? Well, the other options are that here's the nucleus, and then here's the charged particle electron, and it just moves in a straight line. It doesn't end at a constant speed, and so in this case it doesn't accelerate, it doesn't emit light, doesn't lose energy. But if that's the case, then you still don't have an atom, because electron just goes away and doesn't stay within the atom. So this can't be the case either. The third option is that you have the proton that sits here, and then you have an electron, and the electron doesn't move. If it doesn't move, then it doesn't lose energy. But if you just drop an electron here such that it doesn't move, then, well, it's going to be attracted to the proton, and so it's going to move in, and then you have a collapse of an atom again. So you can't have so there's a problem here. We don't really know what the electron is doing. It can't go along a straight path, because then it just moves away. You don't have an atom. You can't just sit there and do nothing, because it's going to be attracted, and then you don't have atoms. And it can't move along a curve, because it would have to spiral inwards towards the nucleus. So the point is that the picture that we have here, we typically show where electrons orbit the nucleus. That's not quite true. We don't really know what the electrons are doing there. The best pictures that we have, we don't really have a picture, but the best ideas that we have of what's going on the inside of the atom is that there's a nucleus. The nucleus is a positive charge, so plus. And the nucleus typically would sit with some, within the nucleus you'd have some neutrons. So let's put some neutron here. We don't really know. That's, well, alright, so there's a nucleus with a positive charge. And then you have a negatively charged electron that sits on the outside of the nucleus. But exactly what it's doing we don't know. However, what we can calculate is the probability distribution of its location. So you move away from the nucleus, and then maybe somewhere here along this path is where you would have, so this distance away from the nucleus, you would have the highest probability of finding the electron. And then as you move away from this location, the probability of finding this electron gets smaller and smaller. And to indicate that, I'm going to put fewer dots. So as you move away from the specific location where electron is likely to be found, the probability of finding the electron is smaller and smaller and smaller, but our calculations indicate that the electron could be just about anywhere there, and could be even closer, but the highest probability of it being would be somewhere here. So we can calculate these probability functions. We can estimate these probability functions where we can predict where the electron is likely to be found, and as long as we can do that, we can predict what is the likely behavior of an atom, and that seems to work very well. All right, now this would be the orbital. So the orbital would be sort of the region in space where the electron is likely to be found. So maybe I'll do something like this. There you have the orbital. Orbital would be the space where the likelihood of finding an electron is relatively high. All right, so we have that as a picture, and then in chemistry you must have taken you must have looked at all sorts of different shapes of orbitals and so on and so forth. But orbitals ultimately is just a probability space, meaning a space where electron is likely to be found, although the electron could also be found outside of those orbitals, as I have indicated here with dots all over the place. Now, so just sort of keep that in, just remember this. But what we need though for electrostatics is we can get away with the picture that is often shown for electrostatics, in that you have the nucleus with a positive charge. There are some neutrons, but they're irrelevant for our purposes. And then you have electrons somewhere on the outside. So let's just draw a bunch of electrons sitting on the outside, right? So maybe I'll put the same number of protons on the inside. Would I put 5? So then I should have 5 here. The electrons sit on the outside, and then this would be the picture of an atom. And it is not it's a useful way of looking at an atom for the sake of electrostatics, which is what we're going to study here. And the reason why it's useful is because it places electrons on the outside and then places protons on the inside. So what seems to be obvious here is that it would be a lot easier to remove an electron than to remove a proton, right? If I want to remove an electron, all I have to do is get to the surface of the atom, take this guy and yank it out, and it goes, and then the electron is gone. If on the other hand I want to get the proton out, I would have to get all the way in to the inside of it, drag this guy out, and try to pull it out. It seems pretty obvious that it would be easier to remove the electron, and in fact it is very difficult to take the protons out of the atom. That would be a nuclear process. It's very easy on the other hand to remove electrons. So for example, if I have a table, let's draw a table here, and then I want to remove electrons from the surface of the table. Now remember, what I have here is these atoms where I have electrons on the outside, so maybe I'll put some electrons here, and then I have protons on the inside. It's difficult to get to the nuclei, so there's that. If I want to remove the electrons, all I have to do is take a hand Fair enough. That's not bad. So you take the hand and you slide it across the table, just like that. And by doing this, what you end up with is a bunch of electrons on the finger, and that you have just picked up from the table. So let's draw these electrons now. They have just, oh wait, hang on a second, I have to switch something. There we go. So now you end up with a bunch of electrons on the finger. And the electrons that you had there before in the table are gone, at least some of them. You picked up this one and maybe this one, and you picked up this one, and you picked up this one and this one and this one. So you can easily remove electrons from it from just about any substance by friction. And I have charged the hand by friction. The hand is now a net negative charge, and then the table has a net positive charge because there are more pluses than I have minuses. But whenever I charge an object into a positive, I'm not adding protons to it, right? So suppose that I have some kind of a sheet here, and I end up charging this thing to have a net positive charge. That doesn't mean that I drop protons on the sheet. That, in fact, that's not that's not gonna happen. What that means is that what I have done is I have removed electrons. So the electrons are gone, and if the electrons are gone, or some of the electrons are gone, then the net charge is positive. On the other hand, if I do have a sheet and I have managed to charge this sheet to have negative charge, what that means is that I have actually added electrons to this sheet, right? So when you charge something, you either add or remove electrons, but when you charge something, you don't add or remove protons, generally speaking, because you could set up some situations where you can actually manipulate protons, but our everyday experience would be such that you either add or remove electrons. All right, so that's the first thing, concept of an atom, and then charge, how you move electrons to or away from objects. Now we have three particles. We have electrons, and electrons would be negatively charged. I would assume you'd know that. We have protons. Protons would be positively charged. And then we have neutrons, and neutrons would be neutral. They have no charge. Yeah, and then electrons, the charge of an electron is 1.6 times 10 to the negative 19th coulombs, C. So C stands for coulomb. That would be the unit of charge. And charge of a proton is also 1.6 times 10 to the negative 19th coulombs. The difference is that one is negative and the other one is positive, but their charges are identical. As far as the masses are concerned, the mass of the electron is a lot smaller than the mass of a proton. And the mass of the proton is roughly the same as the mass of a neutron. So the mass of the electron is very, very small. The mass of a proton is very, very, very large compared to the mass of the electron. The charges, though, is what's important for our purposes, and so you have that. So suppose you have a sheet, and on this sheet you have an excess of charge where you end up with some negative charge, and you say that this charge Q, symbol for charge is Q, is let's say that your charge is 25 electrons. And if you wanted to figure out what that actually is, what is that charge, then you have 25 times 1.6 times 10 to the minus 19th coulombs, and then whatever you get out of it, this would be the actual charge that you would have. So Q is the symbol for charge, and it would have units of coulombs, C. All right, so I have mentioned charging by friction. Maybe I should add something. So charging by friction, in that case, I think that's pretty obvious. You take two dissimilar objects, two dissimilar objects, and you just rub them together. And as a result of that, electrons will move from one substance to the other substance. Which way do these electrons go? So let's say you have an object A and you have an object B, and you end up rubbing them together. Which electrons will go in one direction only. Which way will they go? That is determined by triboelectric series. So let's say electrons go this way. Why is it exactly that they go from one substance to another? So for example, let's say you take a bunny fur and you wrap bunny fur with a balloon. In that case, electrons will always go from the bunny to the balloon. Why is it that the electrons will go from bunny to the balloon? I don't think we know that with certainty. There's certainly some speculation about it, but I don't think we know exactly what is the reason that determines that electrons go from the bunny to the balloon, but we certainly can determine that electrons go from bunny to the balloon. And there's a table in the worksheet that is called the triboelectric series. Electric series. You can look that up. It's page, I want to say 3. But maybe it's page 5. Anyways, it's not too difficult to find, and the triboelectric series will tell you which way these things, which way electrons will move when specific substances are wrapped with each other. You can also charge an object by conduction. So conduction is a little different, pretty straightforward as well. But let's say you take this balloon here. So you wrap bunny with the balloon. There's a bunny, there's a balloon, you wrap bunny with a balloon, and the balloon now becomes negatively charged because it gained electrons. So what you could do is you could take this balloon, let's draw a balloon here, and this balloon has a negative charge, and let's say you have kind of a rat, and let's say you have a metal rat. And then let's say you have a wooden rat. So, that's good. So then you have some kind of a wooden stick. So you have a wooden stick. You take this balloon and you drag this balloon and you attach it to both of these. So let's say you take, hang on a second. You take the balloon and you move it and you touch it against the metal rat. Some of the electrons will move and jump into the metal rat, and then you take the balloon and you attach it to the wooden stick, and some of the electrons will move to the wooden stick, right? It's unlikely that all of the electrons from the balloon would actually transfer, but certainly some would. And so by doing that, by touching it, you conduct electrons into the other objects. So let me deselect this. And so conduction is a process of transferring electrons by direct contact. Let me put this, write this here. So charging by conduction, charging by conduction. That's a process of transferring electrons by direct contact. Similar process happens in thermodynamics. You can heat something up by conduction. That would just imply that you touch two things at different temperatures together. So going back to these two sticks now, we have charged it by conduction, and so this one has gained some negatives. Let's put 3 here, and then this one also has gained some negatives. Let's put 3 here. Now there's going to be a certain difference though between the wooden stick and the metal rat. Now the wooden stick is an insulator. So I'm going to put here, this is an insulator. And in insulators, electrons, it's difficult for the electrons to move from atom to atom to atom. So if you drop electrons in one specific place, they will just stay there. They won't move anywhere. On the other hand, in a metal rat, these electrons can easily move, right? Because this is a conductor. So this is a conductor. Metal is a good electrical conductor. That implies that the electrons can easily move throughout this whole conductor. And so if you dump them here, they'll repel each other until they find certain equilibrium. So maybe what will happen is, let's see, this one they'll spread themselves evenly throughout the whole thing. And so you'll have one here and another one here, right? You dump them at this spot, but then they just push themselves around until they found some sort of an equilibrium. So in the middle, right, electrons will always distribute themselves evenly as far as the geometry of the surface allows for it, I should say. In insulators, you will always have electrons placed in one spot. So for example, if you have, suppose you had a question somewhere on a test and the question looked like this. Now, here are two substances and they were both charged by conduction. One of them looks like this and the other one looks like this. Which one is a conductor, which one is an insulator? It should be pretty obvious that this would be a metal conductor. Oh, it doesn't have to be metal, but this would be a conductor and this would be an insulator. Right? Because here electrons were unable to move all over the place, they're stuck in these two places, and in this case electrons have spread themselves all over the place more or less evenly, so you have a conductor. Okay, so we have charging by friction, charging by conduction, we have insulators, conductors. Let's go on to charging by the concept of polarization and then eventually induction. So polarization. All right, let's move on. Which way should we go? All right, so polarization. Let's just take, let's look at specific cases. So suppose you have a metal conductor, and then let's say you have some sort of insulator. Let's just do this insulator. Maybe it's wood. Although in the case of wood, you have polymers, but yeah. All right. So then let's say you have, and this thing is neutral, right? So this thing is neutral. Same number of protons as electrons, and this thing is also neutral. So same number of protons as electrons. Now you take a balloon and you bring this balloon closer, and let's say that this balloon is negatively charged. So the balloon is negatively charged and you bring this balloon closer and closer and closer to the metal. As you do that, what will happen is the electrons, because there are electrons over the place here, the electrons will move. So maybe I'll draw like a chain here. Here's an atom, chain of atoms, and of course you have more of these chains here, but let's just put one row of atom. You have more of them. The electrons in this atom here would tend to be pushed a bit to the right, and the and maybe maybe from the first atom an electron might actually make a jump to the next one. If that happens, if an electron goes from here to here, then that would imply that there's another electron that is pushed this way and then pushed this way and pushed this way and pushed this way and pushed this way. The end result is that whether the electron actually makes the jump or whether the electrons are just pushed to the side of the atom, that would still induce certain movement in the electrons in the next atom and so on and so forth. You'd have this chain reaction where on this end you'd end up with a negative charge. But on the other end, you would end up with lack of that charge, and therefore this would be positive. And of course, this is going to happen along this whole wall. And this is going to happen along this whole wall as well. So you're going to have these rows of atoms where electrons will end up being pushed to the other side. And so you're going to end up with negative, 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 and then you're going to end up with positive and positive and positive. On the inside though, you're not really going to have any imbalance of charges. You're just going to have an imbalance on this side. It's going to be positive. You're going to have an imbalance on the other side. This is going to be negative. And now what you have is a situation where you have an object that has one end that is positive, the other end that is negative. This is a polarized object. So this has been polarized. That's it. You just sort of induce a separation of charges and then you have polarized the object. Now, in the case of an insulator, this is going to work a little differently. So let's say you take this balloon and you bring the balloon closer and closer and closer. It's a negatively charged balloon. You bring it closer and closer and closer. What will happen is, let's draw it like this. Here's an atom, another one, another one. I'm going to draw only one row of atoms. So you'd have a positive nucleus. So let's put a positive here. You'd have positive nucleus, you have positive nucleus, and then you'd have electrons on the outside. So you have this cloud of electrons. You'd have them here, you'd have them here, you'd have them here, and initially you have more or less even distribution of these electrons. But then as you bring the balloon closer and closer, these electrons will tend to spend more time on this side. And that will cause these electrons to be pushed to the other side, and that will cause these electrons to be pushed to the other side. You're going to end up with, let's see, some of them are gone. So this is kind of, let's say this one and this one is gone. Let's say this one and this one is gone. Let's say this one and this one is gone. So your orbitals would be changed, and then it would be more likely for the electrons that they would be found on this side, and on this side. But note what you've done here is, and these electrons though cannot move. So this electron cannot go to the next atom because this is an insulator, right? And electrons are stuck in insulators within their specific atoms or within their specific molecules. But what we've done is we've polarized each individual atom. So this atom here is polarized, this one is also polarized, and this one is polarized. The two pictures are different, right? You don't really have an even distribution of charges on the inside here within the metal, within a conductor, but within an insulator you do. Right? Because if this was an insulator, if this was a conductor, then these electrons would be able to fill in the blank that you have here, and these electrons here would be able to fill in the blank that you have here if this was a conductor, because electrons could transfer from one atom to another. But this is an insulator, so you end up polarizing each atom, but that doesn't happen in the case of a metal. All right, so that's the concept of polarization. And after polarization, we can charging by induction. All right, so let's do it here. Charging by induction. So the process works. How should we do it? We should do it like this. So let's say you have some kind of a metal. Here's the metal. So it's a conductor. And then you bring in a balloon. And this balloon is negatively charged. So let's put some negative charges here. And first you charge the metal by conduction. And so what you do is you take this, you bring it close and touch it right there. As you touch it, electrons jump into the metal. So some of them transfer, and these electrons now distribute themselves evenly throughout this whole thing. So let's say we had a bunch of them here before, and now some of them have been moved. How many? Four, five. Five of them have been moved. So let's say this one, and this one, and maybe this one are moved. And then, but that's just charging by conduction, right? But then what you can do is you can take a hand and bring this hand to the balloon. Right, so you take that hand, you bring it to the balloon, and you bring it to the metal, you touch it, and what happens here is the electrons go, or at least some of these electrons will jump into your hand. Wait, that's grounding. Yeah, okay, yes. So then they jump into your hand, and I think that will do the trick. So now these, I should have moved it. Oh well. So now some of these electrons jump. So let's say, let's keep it blue. So let's say that 2 jump in here, 1 and 2. So your finger is now charged, but then here these are missing. And that's just grounding. That's not really charging by induction. That's just grounding. Well, anyways, so I explained to you how you ground things. Let's remove that. There it goes. So I guess I should correct what I put up there on the tab, because we basically did something different. Oh, hang on a second. There we go. So what I have explained to you here is what grounding is. Right, so that's not quite what we went after. This was just grounding. To ground something means to provide a path for the excess of charges to move away. So let's say that I have some kind of an object. Let's say I have an antenna. Let's see if I can draw an antenna. Can I draw an antenna? I'm gonna try. Good enough. So you have an antenna, and if you want to ground this antenna, let's say this is a metal, you have metal on the top, and then let's say that this here is plastic or some kind of a wooden stick. So you have wooden stick here, and then this thing is in the ground. Ooh, how am I gonna draw ground? Let's try that. Look at that. Look at that. If you want to there's an antenna. If you want to ground this antenna, what you'll have to do is you have to take a wire, attach it to that, run it into the ground, and then you provide a path for the excess of electrons to move into the ground. All right, so the concept of grounding is something is grounded if there's a path provided for that something where the electrons can move along that path and move away from the object. Good, so we have grounding. But we still have to go over that charging by induction. All right, so if I want to induce a charge in an object, then I have to polarize it first and then ground it, or rather I have to polarize it first and then remove some of the charges. All right, so let's say that you have a metal here and it is neutral, and then you take the balloon, and the balloon is negatively charged. You take this balloon and you bring it to the metal, but you don't touch the two. Right? That's the difference. So you bring it closer and closer and closer. Say this is enough. Okay, good. So you've gotten to this point. What you have done in the process is you have polarized the metal. All right. So there is a shift of the electrons such that you end up with an excess of electrons on this side. So minus, minus, minus. How many do I have here? 3, 5. So let's put like 5 here. And on this side, on the other side, electrons have shifted, so you end up with a positive. 3, 4, and 5. There is no contact. I'm going to put here no contact. You just polarize this piece, so this piece is polarized. Polarized. But then what you're going to do is it's not charge it, right? You end up with 5 negatives on the right hand side and 5 positives on the left hand side. So this thing still has no charge, really. It's just neutral, but you want to charge it. What you will do then is you will remove some of the charge. So you could do it two ways. You could take a hand and that's good enough, I suppose. You will take the hand and you're going to that's a great hand. You can, if you touch it to this side, then electrons will jump into your hand and you're going to end up with a net positive charge in the middle. But however, you could also take this hand and touch it to the other side. Then what will happen then is the electrons in your finger are going to be attracted to the positive charge, and the electrons from your finger will jump into that object, and then you're going to end up with a negative charge in the middle. So let's say you do this though. The electrons will jump into the finger, and so we end up with a picture that looks like this. So 2 electrons have moved in here. That implies that the other 2 from here are gone now. So this one is gone, this one is gone. And if you look at it, what we now have is a net negative charge. So now it's no longer neutral, but it is, I'm sorry, net positive charge. So now you end up with a net positive charge. This whole thing is now positively charged because you have more pluses than you have minuses. This whole process that I have just described, all of this, where you use polarization plus, you know, some sort of grounding, which is effectively what I did with this hand. That gives you charging by induction. And there's another variation of this, and let's see where let's see if I can find some space somewhere. Here, this will do. So suppose that you have a metal and another metal, and the two are in contact, but they're separate. So there's first one and the second one. You take the balloon, they're both neutral, but you take the balloon is negatively charged, and you bring this balloon closer and closer and closer. What will happen is you're going to end up with shifting electrons here, and this whole piece is going to be polarized. I mean, both of these pieces will be polarized, but in this way. And then what you can do, you just polarize this thing, right? So this whole thing is polarized. Then what you can do is you can take, let's see if I can do that. You can take, no, that's not what I wanted to do. This is what I want to do. You can then take this whole thing and move it. It should be pretty clear that you now have two separate objects that are charged. This is also charging by induction. You induce, so this is charging by induction, you induce charge into the two objects. And so then these, because this is a metal, these would then shift themselves around so that you would end up with some kind of an even distribution. So this wouldn't be the case once the balloon is gone. These three negatives would spread themselves, let's say like maybe like 1, 2, and 3, and then the other pluses would do something similar. It's not that the protons would move, it's the electrons that would shift all over the place, but they would shift in such a way that you'd end up with positive charges distributed more or less evenly. Okay, so we have I think most of the basic concepts done here. We have the concept of the atom, electrons, protons, neutrons, nucleus, charge, charging by friction, charging by conduction, polarization, grounding, and charging by induction. All of the concepts are in this video. Good. So this is the introduction to electrostatics. You want to be familiar with all of these concepts, and then there is a worksheet that you can also look through and make sure that it asks. It's a bunch of multiple choice questions. You can go through these and see if you understand the concepts well enough. Along with that worksheet, at some point I'm going to post also the key, I think. Okay.